All right, so we've talked about how to go from the electric field to the potential, the electric potential. Can we go backwards? Can we go from the electric potential to the electric field? The answer is yes, you can. We took an integral from the electric field to get to the electric potential. Do the opposite here to get back to the electric field. We can take a derivative of our electric potential to get our electric field. And the derivative that we take is the negative gradient of the potential. If you have taken multivariable calculus before, you have probably seen the gradient. We'll talk about this gradient in a little bit more detail coming up here. Let's talk a little bit conceptually about the gradient. What is the gradient? The gradient is the derivative in the steepest direction. So what we're going to think about doing is taking a derivative in the steepest direction, and we're actually going to use an equipotential graph to help us visually do this. And the component of the electric field in some direction is the derivative of the electric potential in that direction. All right, we'll see what we mean here in just a second. Like I said, we're going to come back to this equipotential graph. And the question that we're going to ask ourselves is, can we find the gradient on this equipotential graph? And so we want to use this equipotential graph to build the electric field of this. We know this is a point charge. We know what the electric field is. Let's see if we can back out and we can get the electric field out of our equipotential graph here. One of the things that I can write down here is the gradient in Cartesian coordinates at least. And this electric field will end up saying E is equal to minus, and in Cartesian I would write dv dx x hat plus dv dy y hat plus dv dz z hat. Okay. So when I'm looking at my equipotential graph here, remember I've got a point charge in the middle and I have this equipotential graphs where two consecutive lines are telling me about the change in my potential, and the change in potential between two consecutive lines is the same between each two consecutive lines. So I'm going to think about a point. Let's choose a point right here to think about how I can visually grab the gradient from the graph. So if I choose to go in one direction, maybe I'll choose to go in the x direction, I can think about drawing a line from here to here, all right? And now I'm thinking about I'm going to go actually up here to think about what this is telling me. And I'm looking at this component here of my gradient. Now, what I can write is something like, I'm looking at this derivative here, dv dx. I can also sort of think of this as a change in my potential divided by a change in distance. And this is when our graph is going to come in handy to help us see which components are bigger than the others. So right now what I'm doing, if I wanted to calculate my component of the electric field in this direction, I can take my change in my potential, which is going to be the same for any two consecutive lines, so I've got some delta V here, divided by this distance. I could just as easily have gone upwards in the y direction, something like that, and then I can see that this dy is bigger than this dx. So then if I'm thinking about my electric field components in the x and y direction, I might say that because my delta x here is smaller and this delta x shows up in the denominator, my delta y is bigger than my delta x. A smaller denominator means a bigger overall value, so I would have a bigger component of my electric field in the x direction if I'm looking at this point in particular. So that's generally how the gradient can work, but we're really interested in the gradient in the steepest direction. And the steepest direction, I'm just going to erase my lines here. Okay. The steepest direction is going to be when I can make this the smallest. My delta V is going to stay the same. So really I want to find the direction in which my denominator is going to be the smallest. And for equipotential graphs, that's always going to be perpendicular to your equipotential lines. So right away I can see, let me see if I can try to draw this. Something like that would be the smallest distance between these two lines here. If I go perpendicular to your equipotential line to the next one, is where you'll get your steepest descent, right? Okay, so that means that I can go around to anywhere on my equipotential graph to identify what the electric field might look like. So if I come up here, maybe up here, my electric field might look like that. If I'm coming out here, trying to draw it on the line, my electric field could look like that. And then even in here, I might have an electric field that looks like that. Now, we know that this is what the electric field should generally look like if I have a point charge in the center of this graph, right? If this is a positive point charge, I should be seeing an electric field vector map that points radially outwards in all directions from this source, which is sort of what I've tried to draw in here. Now you might wonder, how did I know to choose this direction? And that's actually where this negative sign comes from. The negative sign tells us we want to go downhill from high potential to low potential. And so I know that when I have a source charge here, a positive source charge, I have high electric potential near the source charge, and I get lower electric potential as I move farther away from the source charge. So that negative sign there is telling me I want to move from a high potential to a low potential. The other thing I can think about is, how do I know how big my electric field is at any given point? And I can do that by looking at the closeness of the lines. So notice that if I am somewhere out here and I'm thinking about what is my electric field at this point, sometimes it's useful to look back and forward to get sort of an average in between these two lines. So at this point, if I'm looking at this sort of change in my potential here and this distance there, it's much bigger compared to lines in here. These lines are closer together, indicating that you have a smaller delta x or a delta r in the denominator of your gradient, and so you will get a bigger electric field at the locations where you have more dense lines. This is also true if you think back to the topographical map that I showed you in one of the previous videos. If you're looking at a topographical map, your contour lines, when they start to get really, really dense, tells you that you have a very steep incline really quick. And it's same is sort of true here. My electric field, the density of these lines is telling me about the magnitude of my electric field. The denser the lines are, the higher in magnitude the electric field will be.